Welcome back, and to this session on the more technicalities about the final model which we are going to simulate. So don't be intimidated by this long set of equations, because that is meant more as a kind of background. And for those of you who have taken a course in many-body physics, you may have encountered this Lipkin model, which I'm going to explain a little bit more what it means. We are going to rewrite this in terms of Pauli matrices. Now, the nice thing with this Lipkin model is that we don't need to make a transformation of what is normally called creation and annihilation operators in quantum mechanics. That kind of transformation has a name in the literature, and it's often called a Jordan-Wigner transformation. Now, for a generic Hamiltonian, this is something which has to be done, whereas in our case, this is a simpler type of Hamiltonian, and that means that we can get away with a Hamiltonian which can be rewritten just in terms of Pauli matrices. So what I'm going to do today is to go through these steps so that you see the final expression which we have to program. That means that I'm going to give you these expressions. You don't need to go through all the calculations, but I provide a lot of background material in the slides here for those of you who actually want to look at how we can derive it. So the important thing for us is to have something which is written in terms of Pauli matrices, which we then can implement with the VQE algorithm and find the lowest lying state of. So, however, I have to intimidate you a little bit with some algebra from many-body physics, but you don't need to think about all these things. So those of you, some of you here have taken such a course and you know about these details, and some of you have actually been simulating these things before, and you probably encountered these things. But I wanted to say, before we move on, I just wanted quickly to repeat a little bit about the technicalities which we have to compute for the 1 and 2 qubit case, which we discussed last week. In that case, we had a simpler Hamiltonian type of problem, whereas now we are going to dive more into the basics of what a typical Hamiltonian looks like when you do many-body physics. So it's still simple enough so that we can rephrase everything in terms of chains of Pauli matrices and the identity matrix. Some of you may have encountered a little bit more complicated ones, or some of you may have worked with specifically dedicated spin models like the Heisenberg Hamiltonian, the Ising model, etc. So these are Hamiltonians which you can rewrite immediately in terms of spin matrices. And then when you have it in that form, that is where you have to rewrite that in terms of gate operations. So what we're going to do today is actually go through some of these things and link that with how we want to solve it. And next Wednesday, what we are going to do then is just to sit down and just discuss how we would solve the problem in project 1. So that means that next week, I will only give a brief reminder on what we're going to simulate. And then both Ruben and Karen will be here, and we will basically just work with the project. So that means there will be no lecture topic next Wednesday. Okay, so let me switch over to the whiteboard and quickly remind you of what we did last week. So as I said, I'm going to come back to what you see here. And this provides you with background information on how you can rewrite, as you can see here, a Hamiltonian which is written in terms of creation and annihilation operators, how I can rewrite that one in terms of Pauli X, Y, Z matrices. So let's switch to the whiteboard and quickly remind ourselves about some technicalities from last week, because then we are going to use that when we look at this model. So this model is something you can think of us meeting a first many-body Hamiltonian, which has been simplified, however. It allows only for some specific types of many-body interactions. Okay, so what we did last week was actually to look at the simpler Hamiltonian, where we had the 1 qubit case. Let me just remind you of that. And this 1 qubit case was given by a Hamiltonian which contained a constant multiplied with the identity matrix. It contained a new constant multiplied with a Pauli Z matrix and a final constant multiplied with the Pauli X matrix. Now, one of the things which we always want, since we are using a computational basis, and in our case, the computational basis is typically qubit 0 and 1, and this is an eigenbasis of the Pauli C matrix, then we always want to rewrite, or we have to, in order to make a measurement, we have to rewrite all other combinations of gates, or in our case, these are just matrices, in terms of a Pauli Z matrix. So typically what you will often see in the literature is that the measurement matrix is something which is given by the Pauli Z matrix when it acts on a qubit. Now, this means that you have to find a transformation of any other one of these in terms of that matrix. So that means that there would be some kind of unitary transformation multiplied with Z and multiplied with U, which allows you to rewrite a Pauli X matrix in terms of the Pauli Z matrix, which you then use to project out either qubit 0 or qubit 1. Okay? And in our case, for this specific Pauli X gate, this H is given by the Hadamard matrix. So now I should make this a little bit different from the Hadamard matrix, which is then just 1 over square root of 2. And this is just for the 1 qubit case, -1. No, this is +1 and -1 here. And as you remember, this is something which you can rewrite in terms of a Pauli X and a Pauli Z matrix. And we went through the algebra last week, and we found that we could rewrite the Pauli X gate in terms of that. Then, when we want to implement this VQE algorithm, what we typically do then is that we make an ansatz for the wave function where we rotate a qubit on the Bloch sphere in a random rotation along the x-axis and the y-axis. So that means that we would typically start then so we would get an ansatz for the wave function in terms of an angle theta and phi. And this would then be given by us if we now assume that the qubit 0 is the lowest lying state. We also have to pay attention to something which we haven't discussed much, because we've been only looking at simplified Hamiltonians. When we come to this Lipkin model, we have to pay attention to the fact that we want to have a lowest lying state which has an ansatz with the same type of symmetry. So that is going to be a difference from what you've seen before. Because in the 1 qubit case, it's either qubit 0 and 1. We would typically start with qubit 0 if you assume that that's the one which is giving rise to the largest or the lowest lying state. So we would have a rotation along the x-axis and the y-axis. So we had a theta, and then we had a rotation Rx like this, acting on the 0 state. That means that we would set this up as a set of gates. It means that we would then prepare the state like this. This is fed into a Pauli X, actually a rotation along the x-axis. So we have an angle, and then we have a new rotation of theta, and this gives us a state which is now modified. And I'm just going to write it like this, prime here. So that's the modified state. So this is a typical setup when we now just were dealing with 1 qubit. And last week we went through the way we would set up the code for that and how we would run the VQE algorithm and then find the optimal values for the angles. That's the variational part. So this was a semi-classical or classical quantum computing algorithm. So we would do the quantum computation with the gates, setting up the rotations, etc., etc. And then we would perform the optimization part where we find the optimal parameters by just calling a classical algorithm. And that would do the optimization for us. And then we would run the measurements. We collect all the measurements. And with that, we find the final expectation value. So that's a kind of basic recipe which we outlined last time. Now, the other algorithm which we had, with the other system which we had, was given by this 2-qubit Hamiltonian. And in that specific case, what we had, so this is the second Hamiltonian. And in that specific case, we had written a Hamiltonian in terms of Pauli X and Pauli Z matrices. So we had defined an operator H0, and that H0 acts on these states and gives an epsilon 00 of 00. This is the non-interacting part of the Hamiltonian. And this defines our computational basis. So I'm just repeating some of the things we had last time because that makes the link with these more simplified Hamiltonians with what is coming now in terms of the Lipkin Hamiltonian. So the final one is given by this one, and we have Ed, and then 1, 1. So these are the computational eigenbases which we have, which means that the solution then should be given in terms of a linear combination of these computational eigenstates or computational states. Then we defined a interacting piece, H1, which was given by some constant. And then I had a Pauli Z, which is a 2x2 matrix, another Pauli Z matrix. So this is now just given by 4x4 matrix. We have 4 qubits in this case. 2 qubits, plus an H of X. And then we had X, the Pauli X matrix, tensor product with another Pauli X matrix. Now, one of the things we did then last time was actually to rewrite this H0 term. So we rewrote H0 in terms of some additional terms. So we wrote this H0 as a linear combination of all these kind of 2 qubit energies. So we could rewrite that one in terms of an alpha multiplied with the identity matrix. There was a term beta multiplied with the identity matrix times the Pauli Z matrix. So remember now that when we write this in this specific form, these are 2x2 matrices, and they represent tensor products. Just keep that in mind, right? So when we use this kind of shorthand notation, this is actually a 2x2 identity matrix, tensor product with another 2x2 identity matrix, and that gives you a 4x4 matrix. Because now we are going to have 2 qubits, and we have 4 computational basis states. Okay? Then we could rewrite it in terms of these different Pauli matrices and the identity matrix, plus a parameter delta of Z times Z. So I'm just going to rewrite. So these terms which we have, these alphas, betas, and gammas, and deltas, are just linear combination of these different energies. And this is what we set up last time. So let's, if everybody's okay, I'm just going to switch page. So just to give you these parameters, so they are linear combinations. So we have an epsilon 00 plus an epsilon 01. And when you add these up, you will see that this actually gives you the final diagonal elements. think that is plus an epsilon 1, minus an epsilon 1, 0, minus an epsilon 1, 1. And finally, you have a delta, which is an epsilon 0, 0, minus an epsilon 0, 1, minus 1, 0, plus epsilon 1, 1, divided by 4. And when I add all these terms up, I'm going to get this final matrix which we have. So the final Hamiltonian which we have in this case is now going to be given by this parameter alpha times these two identity matrices plus the parameter beta times the identity matrix times the Pauli Z matrix plus gamma times Z of Y. And then I have plus, and now I have this diagonal element delta plus this HC. And this has a CZ operator plus a parameter X for the X part, which is given by this XX guy. So these are the kind of gates which we actually need now, or these matrices which we need to transform into a measurement basis. So if we look at the different combinations which we have, so we would like to transform this set of I into something which is given by some U times Z times U. So we need a specific transformation. And let's just put an index P here to indicate that this is just one of these combinations. Yeah? Yeah. So this will also be a 4x4 matrix actually, but it will act. I'm going to show you examples on what it's going to look like. So, yeah. The upper left or the lower left? Yeah, yeah, yeah. I will show you some explicit examples now, and then you will see very clearly what it looks like. So the kind of transformations which you have, if you now look up a table for these ones, you would see now that this U, so Z times I, that has this U of P, which is actually equal to the identity matrix times the identity matrix here. So that is pretty simple. And the, yeah. No, because this becomes, you will see now that what you're going to get now are just matrices which you're going to multiply with. So in the previous case, what you see here, this should not be written as just a Z matrix. I should take that one. Let me just be a little bit more precise. I define this matrix M. So that is better. So that's the matrix for making the measurement. Yeah, that is also tensor product now because yeah, you mean that I should write the tensor products here, right? Yeah, I know. It's this is just a kind of more compact notation, and you will see that that becomes more useful when you're having many. Okay. So, but what we mean, no, so this can, I agree that this can be a little bit confusing because what you have here is a matrix times a matrix times a matrix. This becomes, being a 2x2 is a tensor product with a 2x2, so that's actually a 4x4 matrix. So it's a little bit, how to say, compact notation here in the sense that we skip the tensor notations. Yeah, that's a good point. I know. So we should in principle just write this like this. There is some kind of sloppy notation in the literature in the sense that it becomes difficult sometimes when you see an expression like that. Because that is an explicit matrix multiplied with another matrix, multiplied with another matrix. That's a good point. So I will try to use a tensor notation, But sometimes when you get many strings of these Pauli matrices, then what happens is that people just shorten it down, and then you have to implicitly understand from the context whether this is a tensor product or just a matrix-matrix multiplication. So this is like when you go into textbooks in statistics, there will often be a footnote which says simply that the reader should understand from the context whether this is a vector or a matrix or a scalar. And we will not use any boldface notation or any such notation, but the reader should understand from the context. That is very frustrating. So I agree fully. I will try to be a little bit consistent here. I guess there's a factor of human laziness coming in here, or notation reduction. So the Z tensor product with the identity matrix. So that means that one of the reasons we write it in this specific order is that this will act on qubit 1 and this acts on qubit 2. So if nothing happens with qubit 2, we just label that with the identity matrix. So if we then move into the I dot product with C, that has something which is called the swap matrix. And this is something I have to identify now. So it has U of P equal to the swap matrix. So this is a very important operation which we haven't discussed yet. So we mentioned it briefly last time. So let's take a closer look at what that could be. But let me just fill in the final ones, because this is something which we will find useful also when we look at the Lipke model. So I'm just making the list here. This has something which is called the CX. So this is a C not gate, but it's different from the one, yeah? Yeah. No, it's the same. So when I I should write. Yeah. But sometimes I should write it like this in more compact. Yeah. Thanks. So this is something which is called the CX10 matrix, and I'm going to set that up. And the X, and those code examples which I showed you last week, they have actually these examples baked in. So you can look up the codes which you find online and take a look at them. I mean, if you look back at the links we had last week, and this is given, this one has the following transformation, which is a CX10, and then it has a Hadamard, 2x2 Hadamard. So these are 2x2 Hadamards, which are then tensor producted with each other. I'm going to show you some of these operations now, and then you will see what they actually are doing. So if I take the swap gate, what is the swap gate doing? So the swap gate, if we now take this matrix, which is I times Z, that is the same as 1, 0, 0, 1, and then it has a tensor product with 1, 0, 0, minus 1. So that is what we are setting up. And if you then look at what you end up with, you end up with something which looks like this. So we would have 1, 0, 0, minus 1. And then we have a block with zeros because we are multiplying this guy here with that matrix, and it has zeros in front of it. And then we have 0 here, and then we have a new sub-block here, which goes like 1, 0, 0, minus 1, like that. Okay. Now, if I now look at this swap matrix, so the swap matrix, if you now take a look at it, let's just write it down first, the matrix. So this looks like as follows. So we have 0, 0, 1, 0, 0, 1, 0, 0, and then 0, 0, 0, 1. So if you take a closer look at that one, what it is doing for us is if I act with the qubit states 0, 0, that doesn't change that one, because that's the same as taking that matrix and multiply that one with 1, 0, 0, 0. And that simply gives us back the same state, because we have a 1 there. If you then act on that one with the 1, 1 state, that gives us also the 1, 1 state back again. Because the 1, 1 state, just to remind you of that one, is the same as 0, 0, 0, 1. And the only element which acts on that one is this one, that one here. Now, what happens next if I act on the state 0, 1? What it does, it swaps the qubits. So I get 1, 0. And you can see that if you now just recall that 0, 1 is equal to 0, 1, 0, 0. And if you multiply it with that swap matrix, you actually interchange this one and place it here. So you get from a 0, 1 to 1, 0. So you swap the two qubits. And it shouldn't come as a surprise then that if you take the final one and you take swap 1, 0, that gives you 0, 1. And you will often see this depicted in a specific way in quantum circuits. So the way you would see it is something like this. You have two qubits, and then you have this operation. So you're actually swapping these two guys like that. So if it's a 0, 0, nothing happens. 1, 1, nothing happens. But if you have 1, 0, 0, 1, then you interchange them. And it's often written in the following way. So it has an X here and an X here. So if you now make this transformation of that specific element which we were looking at, this one, then if you look at that one and now multiply it with the swap gate and the unitary transformed swap gate, what you end up with then, if you perform the operation, if you take now a swap and then you multiply it with the identity matrix, and keep in mind now that what you're doing is a matrix, matrix, matrix multiplication. So if you do that with a swap, and you do the algebra, what you get then is 1, 0, 0, 0, and then you have 0, 1, 0, 0, and then 0, 0, minus 1, 0, 0, 0, 0, and minus 1. So that's the final matrix. And then you will see now that when you act on these different states, so if you act with this operation here on the qubit 0, 0 combination, you will just get plus, which is the correct value which you would get when you make the measurement on one of these qubits. Then, if you multiply that one with the 0, 1, you will also get plus times 0, 1. If you multiply this one, so if you take this combination here, and you take this matrix, so let's just call this a matrix in the measurement basis. So if I take that one and multiply that one with 1, 1, that is going to give me minus 1, 1. And this is what I want. If I act on 0, 0, I get plus 0, 0. Okay? So I have now transformed this one into the basis which I'm interested in for making measurements. Yeah?
Our space is
Let me see now if you understand the question. Could you say it again? Yeah. So you mean there should be a -1 here? Is that? No. Yeah. Yeah, right. Okay, let's do in the break and then correct it. Is that okay? Okay. Yeah. I always need to redo my algebra. Yeah. Yeah. What do you say, Ruben? Yeah. 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 Okay. Yeah. Okay. Let's try to take that in the break and just go through the math again. Yeah? If that's okay with everybody, because this is something which sometimes on the whiteboard here, I just confuse myself. I thought I did it on the notes, but let's take a look at it in the break. Okay, good questions. Now, the other matrix which I wanted to present to you is this CX10, and that matrix, I'm just going to give you the form of it, the mathematical expression. This is a 0, 1. So the CX not gate, so this is actually the opposite of a standard C not gate. So the only difference now is that we have the identity matrix here. So when you normally see that one, you see this in this term C naught, which is often written as a CX or just a CX01. And that means that this is given by 1, 1, 0, 0. We have a 0 block. And then we have in here, we have a 0, a poly X matrix, like that. And that's the one which brings the gates which we had for the matrix elements. If we now look at this Z dot cross product with tensor product with Z, the matrix which transformed that one into the measurement basis is now this CX10 matrix. And there are tons of such combinations. So I'm not asking you guys to cook them up. We will give you these combinations because there's a long, long list of different such expressions. And they translate into different types of gates. Now, one thing I wanted to say a little bit about when it comes to the way you prepare the states in the VQE for the 2-qubit system. So the VQE, we looked at the VQE ansatz for 2 qubits. There are many ways of doing that. And one way which is often used, and you will see that in the article by Tilly et al., is actually to rotate the 2 qubits individually and then to entangle them through a CX gate or any other operation which can entangle 2 qubits. So you can do the ansatz. So a typical ansatz is now to have these different angles, theta 0, phi 0. You have a theta 1 and phi 1. So this is for 2 qubits. So that means that if we have n qubits, we have 2 times n parameters. So with n qubits, we have 2 times n variational parameters. So clearly this becomes quite a lot if you increase the size of the system. Now, a typical way to do that, so preparing the state, is as follows. So you would normally prepare that with a 0, 0. If you assume that that is a good ansatz for the lowest lying state, so you would have a 0 here, and then you would rotate it along the x-axis. So you have an Rx of theta 0, and then you have an angle here, an Ry of phi 0. You do the same with an x qubit, and you would then have a theta 1, and then you prepare it again here with a new rotation, and then you have a phi 1. Now, what is pretty common to do then is to actually entangle these states, make a linear combination of them. And you will see that in many cases, we can play around with different type of initial states. And this is something which will become useful when we are looking at this Lipkin model. Because then we would like to have an initial state which has the same symmetry as the ground state we are targeting. So what could be done then is that you entangle it. So you could have a C NOT gate. So you could do that, and this is normally marked by this. And then you would have a new state. So that would be your initial state, which you then would use in the variational quantum eigensolver. So then you would have an entangled initial state, a linear combination of the different qubit states. This is just one way of doing it. Later, you will see another way of preparing a mixture of the different computational basis states. So this is a typical C0 operation. You could, if you wanted, you could simply have that as a tensor product of these two rotated states, and without doing that entanglement. So this is very much up to you. And people choose different ways of doing that. Which one is the best one is something which depends on the specific case you're looking at. Now, what I wanted to do next, so this is about the 1 qubit and the 2 qubit Hamiltonians. So if you look into those code examples, you will see ways by which you can set up the initial states and also actually prepare the system and set up the different gates which you need to deal with, because for the 2 qubit case, what we have to do now is simply to rewrite the Hamiltonian in terms of this different combination of Pauli C, Pauli X, and identity matrices. Any questions so far? Yeah?
Yeah, I want to ask you.
Yeah. So the C gate is often the way you can think of the system interacting with an external measurement, which in that case is often a laser, which is pointing at the system. So you would then have to decide what is your computational basis. And a typical quantum mechanical system, you would often find the lowest lying state of the system. This could be the ground state and an excited state. And these are the states you want to build upon in order to perform the quantum simulation. So when you are targeting a specific system like ion traps or quantum dot systems, you're looking after states which may be long-lived and which have well-defined excitation energies, which also match the electronics which you have or the equipment you have to make measurements. So typically you would excite the state from the lowest lying state to the first excited state, and that would be your qubit 1. So it depends very much on the type of system you have at hand. So one of the things which you would often do then, just to give you an example of a 2 qubit system, this is something which many groups are studying experimentally. So if you have a system like this, it's a often called a quantum dot or an ion trap or something like that. Ideally, you would like these systems to be isolated. So that means that you could think of this as system A, and this is a system B. Normally, there are interactions, there are couplings to the environments, and so on. And the other ideal thing is that you would like to have, let's say, two well-defined states in each well. So this would be qubit 0. So because you want to make a realization. So theoretically, it's no problem in finding such systems. But experimentally, this is actually the difficulty, because these systems will also couple to the environment, and that can give rise to noise and many, many other unwanted things. And then you would have a similar case here, where you have this as qubit 0 and this as qubit 1. Now, in principle, what you have are many, many more states. So the kind of ideal which you have now is that you could have a particle here, and you could have another particle here. Then, since these are isolated systems, you could act on this system with a laser, and then you would produce an excited state, so that this would move up here. And that would live there for some time. So that case would be now 0 in system A, tensor product with 1 in system B, or what we call 0, 1. You can make linear combinations, because sometimes you may not know, you can actually prepare a state which is in a combination of 1, 0 plus some coefficient times beta of 0, 1. And then you're making a measurement. And typically a measurement is actually the system de-exciting. Perhaps if you are here, it could go back to the ground state, and then you would be back to 0, 0. And the measurements you make are typically often done in this specific case with lasers. And the reason why you want to think of these systems as almost isolated is that you are hoping that this system here is not affected by, let's say, a laser which now manipulates this state here. So you want, if these are, for instance, single electrons, you want them to be identifiable, so that you know that electron A is here and not there. So one of the problems which you often face is that there can be thermal excitations, and then this state can end up in one of the higher excited states, and that ruins your computational basis. So you're often looking after experimental realizations where these states here are well defined, and you can label them as a computational basis state 0, computational basis state 1. You can have more states, and that's actually called qubits. So you can have more and increase your computational basis. But the traditional approach has been to have bit 0 and bit 1. Yeah. It could collapse to one of these states. So you make a measurement, if it's, suppose you make a measurement here, that means you act on that qubit and that qubit, then it would collapse into either 0, 1 when you make the measurement. So that means that you pick out a specific state. That's your final state. So the whole idea with the measurement is that you end up in a state which you know is well defined, and then you simply count all the times this state appears. Yeah?
Does it have to be a basis state?
No, the basis. So the thing is that typically when you operate with lasers or gadgets like that, that is something which would typically act on specific types of states, like the state 0 and 1. And you could rewrite the operation of an external probe in terms of a Pauli C gate, which is often the simplest one.
Yeah. It will sort of result in a photon, so sort of in electricity.
Yeah, exactly. Yeah. So the whole thing, or the holy grail, experimentally, and when you want to make the system, is to have states like these, which are well defined, hopefully this is a state which can live long enough so that you can perform operations with external probes and manipulate the states. So one thing we could discuss after the Easter break is how we can make a real simulation experimentally for one of these simple Hamiltonians which we have. So that is one possibility. So that means that how do we actually set up a measurement and find the lowest lying energy using a system which, for instance, could be electrons which are trapped in these cavities. So that's one possibility which we could look at one path after the Easter break. Ruben is going to propose one which deals more with quantum machine learning. The other one is to discuss how we can implement specific algorithms, which we haven't discussed here, because now the focus has been on the VQE and simulating quantum mechanical systems. If somebody is interested, we could actually look at how we simulate in real life a quantum mechanical system. So that means that we would have to make gates like a swap gates, C-NOT gate. How do we actually make them? So that's one possibility for the path after Easter. So that would be a continuation of project number 1. So I'm just mentioning this now because I wanted to bring it up again the last week before the Easter break. And then we will try to summarize what we have done in project number 1. I went a little bit over time. We should also look up these swap gates. So to clarify that one during the break. But let's stop the recording now and then we just take a small break. And then after the break, we look at the fantastic Lipkin model. So if we now look at the next model, which is something which is called the Lipkin model. This is a very popular model, and you also have the reference to a scientific article where people have modeled the Lipkin model with the same kind of recipes which we are going to apply. The model itself is, in the case we have 2 particles, or we can call them for 2 qubits. So the n equal 2 case, we can interpret these as particles or qubits. If we have a system with 2 levels, and one level corresponds to a system with spin down, and the other one with a spin up. We then have slots here. So let me just mark them like this. And these slots have specific quantum numbers. So I'm going to use a quantum number here, mj, equal to -0.5. And then I have an mj equal to +0.5. Now we have slots here with p equal to 1 or 2. So this would be, we would have a similar state here. So we have a slot 1, slot 2, 1 and 2. And then these states have quantum numbers mj, which are different. But these numbers p, 1 and 2 are the same for both these levels. And then we have an energy. So this specific state here has an energy which we just label as a minus epsilon divided by 2. And the next one is a plus an epsilon divided by 2. We can then, and this is a traditional way by which is done in quantum mechanics, is to rewrite everything in terms of what is called a Fock space, F-O-C-K. And that is a space where we typically take away the spatial degrees of freedom, and we simply count the number of particles which are present in different quantum mechanical states. So that means that you can write this Hamiltonian in a very specific way. So you would have a Hamiltonian H, which for this specific case is now given by a factor of 1/2 in front of here. And this sums over these quantum numbers nj and also the states p. And I would have an operator for the spins. So it has a specific quantum number mj here. And it has a creation and annihilation operator, mj, dagger, and a. So for those of you who are more familiar with quantum mechanics and have taken a course in many-body physics, you may have encountered this formalism. So this is, you don't need to know anything about this for the project, but I'm setting it up as a kind of background information so that you have a more complete picture. So there is an interaction piece where you still sum over these numbers, and then you have a p and p prime. And then, so we have a constant interaction. The strength for the interaction is constant. I have an a p dagger of mj. So that means that these two states have to be in the same lowest lying state. So I'm going to explain to those of you who are not fully familiar with this, what it actually means. There is now a p prime minus mj, and there's a destruction operator p of minus mj here. So there is a further term which I'm going to add, but I just wanted to say something in a kind of pictorial way, what this means. So if you look at these two terms, what that means is that if you now have one particle here and one particle here, you see that they have the same values for mj. So it means that these operators here, they take away two particles here. We say that they destroy two particles and they create a hole or a vacancy. Then what this is doing is that it then creates a pair again, but you see now that the states have changed here to a new mj, and these mj's have to have the opposite value of the other ones. So what is this term doing? So if we now look at the system, so before we list the final term, let's now just look at what this V term is doing. So you could think of having two particles here, and they both have spin down. Then you would destroy, so this is where you start. You destroy that, and then you create what we would call an excitation, where they have flipped the spins, and they are now in this state here. So in the many-body jargon, this is called a two-particle, two-hole excitation, because you leave two vacancies here. So these are becoming hole states. That's a pictorial way of thinking of it. And then you create two particles up here. So this is an excitation of the system if you now think that this is the lowest lying state. That means that you're thinking that the ground state is dominated by this contribution here. So when you add this term here, then you're going to create correlations and you're going to create interactions between different states. So if you do the combinatorics and place these particles, you can have this possible state and that possible state. So this is very much like the 2x2 system which we looked at. So we have two possible states which we can create with this operator. This is the kind of pictorial image which one can make out of this kind of systems. There is another term as well. So let's just put a parenthesis around that one. There is a final term which goes like minus, and this represents another type of interactions. So there is still a sum over these mj states, but now we are having this p or p prime, and then I have an a of p mj dagger. So this is creating a state here, and then it has a p prime minus a minus mj state, and then I have an a over p prime in an mj, and then I have an a p here. So that should be a, let me just look at my cheat sheet here so I I'm not saying something wrong. Minus, exactly. And this should be a P, and it has a minus mj here, minus mj. What that means, if we now look at the same type of system, so we would start with a state which has a specific spin. So you could think of this, since this has now a mj here and a minus here, your initial state could be something like this. So you would have one here and one here. So this will be P and this will be P prime. And they have opposite spins. So that's where you start. And what this operator is doing now is that it's actually destroying a particle here and destroying a particle here. And then you may end up in something which looks like this. Okay, so it moves over to a new type of configuration. So these interactions can then create or destroy two particle states and make a new two particle state. Or if you use this language of the states below, since these are fermions, so below the Fermi level, you can think of this as a one particle, one hole excitation. So that's a kind of way you can interpret this one. So everything here is more for those of you who are more many-body aficionados. But normally we don't need to think of this when we are looking at this specific Lipkin model. Yeah. Yeah, this should be a prime term here. There is no prime here. There's just a minus mj. No, the prime has to be to that one, because that has to do with the fact that these are operators which act on fermions. So you think of why you have a P prime here and a P prime here?
Yeah.
Now, the reason is that if you look at these operators written in second quantization for systems of fermions, so you would have, for a system of fermions, you would have a matrix elements like this, an alpha, beta, V, gamma, delta. But when you set up the operators, it would be an A alpha, an A beta, but then you would have a delta and a gamma. And that follows from the fact that this is a system which has to obey the fermion antisymmetry. If these had been bosons, then you would have had the opposite. So this has to do with the fermion antisymmetry. So it's a technicality. That one, yeah. Yeah. In the picture here. Yeah, but this was just a, yeah, I could have changed them, you're right. But remember now that you have an MJ, so you could have a P with a spin down, and then or rather, this could be a P, if this is your P, then you could say that MJ here is the one with the pointing up, that's a positive value. And then the one you end up in has to have the other P prime here, but then it has a negative spin. So the state which you have here, this would be mj, and that would be minus mj. Yeah. Yeah. Okay. Yeah, we don't need to think of this when we're looking at the project. Now, in the Jupyter notebook, you will see an extensive manipulation of these equations where we actually rewrite this Hamiltonian in terms of what are called angular momentum quasi-spin operators. So you can rewrite this Hamiltonian in terms of the same angular momentum operators which are used to from before. So you can rewrite it in terms of epsilon half times j z, which then is something we will rewrite in terms of Pauli C matrices. And you can rewrite the next term, and I'm going to give you these equations and show you how you can get at them, j minus squared. So these are combinations of the jx or x matrices and y matrices. And then you have a minus a w of j plus j minus plus j minus j plus minus n, which is a number operator. And this n counts simply the number of particles which are present. So when this one acts on a state, that one here, that simply gives you as eigenvalue the number of particles which are present. Now, you can then use this one to actually rewrite everything. So these operators which you have are operators which we can actually rewrite in terms of Pauli matrices. So this is jz, which you have here, is going to be given by a summation over the number of qubits which we have, I equal 1 up to n. And this is going to have a Pauli C matrix. This J plus, and we have a specific commutation rules for them as well. This is I equal 1 up to n, and this is given by an x of I, Pauli X matrix acting on qubit I, or particle I if you want to. And this is I of y of I divided by square root of 2. So that means that we can actually rewrite the whole Hamiltonian in terms of this Pauli X, Pauli Y, and Pauli C matrices. So what I'm going to give you are the expressions which you have to program with the VQE. Now, in the Jupyter notebook, you will see an extensive elaboration of why you can, yeah? This is just an index here. So this is I here. This is obviously the imaginary I. So let's take away the dot here and just write it like this. Okay. This is X operating on qubit I, and this is Y operating on qubit I. So when we then, so you can manipulate that one. And if we now look at the case with the kind of operations which we will end up with when we look at this specific Hamiltonian, when we plug in these expressions, it means that you can write it, and I'm just going to give you the expression so you don't need to go through all the hassle, because these are the expressions which we need to implement with the VQE and in terms of gates. So the Hamiltonian then is going to be given in terms of the following expressions of a half, and then I have, because now I have to plug it in the Hamiltonian here, and then I have a sum. So this runs over the number of qubits, the number of particles. It's minus V divided by 2 here, and now I have a double sum. I have to be a little bit careful. And what I get then is an xi, xj, minus a yi and yj. And then I get minus w divided by 2. And then I have a similar one, and you can actually rewrite that one in terms of an x of I, x of j, plus y of I, and y of j. So when you perform the multiplications here. So this is going to be the Hamiltonian we are going to encode. Now, let me bring back, so I will put this into the into the lecture notes so you can see everything. You will obviously have access to the whiteboard notes. But let me try to ruin the rest of the afternoon for you with some algebra. So I'm not expecting, since not everybody here has a background in quantum mechanics, the way it's often tailored in many body physics. But I just wanted to show you how you can show these different operations here. So one thing, so what you would do then is actually to write these operators, since these are acting on one qubit or one particle at a time, you can write them out as quantum mechanical operators in second quantization with the creation and annihilation operators. And this is the way you would write them if you define them like that. They are normally called quasi-spin operators. And you have that J squared can then be rewritten out as this combination which you have here. So what you can show then is that with these operators, you can, one, show the commutation relations for angular momentum. So there are specific commutators which have to be fulfilled for commutation relations. And what you will see now is a very, very interesting exercise where I actually show this. So if you have time to waste this afternoon, you can always go through this. And, but I just have this material just for the sake of completeness, so that you don't feel that I'm just giving you something which, how to say, just taken out of the blue. So here you will find the demonstration of the commutation relations. You have specific operations here. And if you scroll down, what you will see is that you can rewrite. There's a lot of exercise, lovely exercises here. You use these operations, and then you can show the standard commutation relations for quasi-spin operators. So you can rewrite. The thing which is nice with this Hamiltonian is that we can actually rewrite it in terms of these operators, which means that we can then translate it into Pauli X, Y, Z matrices. Else, if we have a more general Hamiltonian, we would have to perform something which is called the Jordan-Wigner transformation. And that will give us many more combinations of Pauli X, Y, and Z matrices. And you would not, you would hate me if I were to give you a more general Hamiltonian for this project. And so these, you will find the different commutation relations. What you will also see is that when you do that, you can rewrite the Hamiltonian in terms of the expressions which I showed you. So there's a lot of algebra here. So you get this term, you can have the second term, and you can rewrite that one as this, as I showed you on the whiteboard. On the whiteboard, just gave you the expressions. Here you will find the derivations of it. So as I said, this is not a very exciting thing, but at least I put it here for the sake of completeness. And then you can also show that these are good quantum numbers, which means that the Hamiltonian commutes with J squared. So that means that angular momentum is a conserved quantum number. And the same thing, it commutes with JZ. So you can actually, you have a long exercise here. You can ask why I did this. I did it just for the sake of completeness. And Louis here and Joseph, they've actually done this exercise. And after that, they just put some kind of, they were not too happy. No, I think you liked it, right? Yeah. Okay. Anyway, what we can do then is actually to use lowering and raising operators, and you can then set up, because now with the 4 particles, I showed you the 2 particle cases, but you can do that with 4 particles. You can actually have a total angular momentum, which is 2, which means that you have 5 projections, -2, -1, 0, +1, and 2. That means that you can actually set up your problem for 4 particles as a 5 by 5 matrix. So when you translate everything, you end up with, so you have all the algebra here. So this is a Hamiltonian matrix, which you would need to diagonalize if you have 4 particles present. Now, this is the matrix which we are going to manipulate. And we are going to make life a little bit easier. And you will see now that if we make life a little bit easier, we could actually take away this W. So we would have a 0 here and a 0 here. And that simplification is actually going to allow us to rewrite this in terms of a 2-qubit problem. The 2-particle problem with this kind of simplification by putting W to 0 is going to just become a 1-qubit problem. So we can have some simplifications which make life a little bit easier for us. Yeah. Yep. So a general interaction would allow you to excite in all possible states. But now you're just limiting the type of excitations of the system to some specific type of excitations. So let me just go back to the whiteboard because that's a very good question. So if you look at this term which we have, this V term, that V term, what it is doing, it takes an initial state here and it promotes 2 particles up here. So that would be a 2-particle excitation. If I have 4 particles, so let's just look at the V term with 4 particles, because the case which we mentioned is with J equal to 2, that corresponds to N equal to 4 particles or 4 qubits. That means that you could make an ansatz for the ground state. So this is the spin up case, and this is a spin down. You have the same separation, but now you would have 4 particles here. So you would have a slot here, P, 1, 2, 3, and 4. Now, U interaction is now of a 2-body nature only. So if you think of the gravitational force, that is a 2-body interaction. It acts between 2 planets at a time or 2 bodies at a time, because it depends only on the relative distance between 2 objects. So this 2-body interaction which you have, that could now produce a new state. And this new state could now be us leaving the 2 first ones here. And then I could promote them up here. So that means that there will be a vacancy here. So you have created 2 slots which are vacant, and these are normally called hole states. So in the many-body physics jargon, this will be called a 2-particle, 2-hole excitation. So you're acting at 2 particles at a time. So this term V acts always on 2 particles in the same spin state, and it can promote them to 2 states with the same spin states. But it cannot have them left in the same state as they were. So it changes actually. So it forces 2 at a time to be promoted up to a higher state or to be de-excited back to the ground state. So this would be a new state. And if you now look at the total spin here, if you add the spin values, because you have 4 particles, you would have that the total spin here is -2. Because you have -1/2, -1/2, -1/2, -1/2, and that is -2. If you, on the other hand, have everything up here, this would be a state with an mj equal to +2. So these are the maximum values. And you know that when you do this kind of spin stuff, that will be given by -j +1 up to 0 +1 and all the way up to j -1 and up to the total j. So when we say that the total angular momentum or spin is equal to 2, this has simply to do with the fact that we can now create these states with the projections which take values from -2 to +2. And we have 5 such states. That is our basis, the 4-particle basis. And then we can set up a 5x5 Hamiltonian, which is the one which we can diagonalize and get the eigenvalues of. So I know that I'm throwing many things at you, but I hope at least you see some parts of the woods for the tree. Now, this state which you see here, this one, the one here, you have now, this has an mj equal to 0. Now, the other part of the Hamiltonian, so this was the part with the v. If you then take the part with w, if we look at that one, what that can do for us is the following. So I could still start here, like that, but that could promote me to something which looks like this. And then I have that one. That would be a state which now has mj equal to -1. And similarly, I could start with a state here, could start here, and then move down to this state. And that would give me an mj equal to +1. So these are the possibilities I have for the spin projections, and there are 5 of them. I know what the stretch state looks like. The stretch state means that I have all particles in one state, single particle state, and there's only one way I can make that. You see, if you look at this one, I can only make this organization here in just one way. But if you look at the state with mj equal to -1, I can make that in many ways, because I don't need to promote this one up here, but I could have taken this one, or I could have taken that one, etc., etc. So that means that they do not have a unique representation. So when I want to build them up, that's when I use these raising and lowering operators to set up the right states. And you will find that algebra in the Jupyter notebook. So feel free to take a look at it, because the final matrix which we end up with is going to look like the one you see here. This is a final matrix, but we are going to make life a little bit simpler. So we are going to put this W equal to 0. And this W is the one which makes a one particle, one hole excitation physically. That means that the states with mj equal to -1 and +1 will not be there. So the only states which then will be interesting for us will be the states which give the projection -2, 0, and +2. So we need only 3 states if we take away W instead of 5. And that's going to be a simplification. If we now take the computational basis with 2 qubits, that gives us 4 states, 0, 0, 0, 1, 1, 0, and 1, 1. And then we could just take 3 of them and use them as a computational basis. So that simplifies the problem. So let me show you how you can do this when you only have 2 particles. And so let's go back to the, so all the kind of algebra here is actually given here. You can diagonalize, obviously. So when you, after you've done all this quantum computing stuff, and you go back to the simple case, which you diagonalize in a blink of a moment, then you would ask yourself, why is this guy forcing us to rewrite everything in such a complicated way? Okay, so at presently, the things we're doing with quantum computing cannot compete with many of the standard methods. But it's a useful exercise to redo it so that you see where the bottlenecks are. I think the most important thing for us is to have a critical attitude to what is going on and to know the pros and cons. Okay, so when we now go to the two-particle case, that means that we have a simpler Hamiltonian. So if we take n equal to 2 here, and we also put this w equal to 0, then we can show that the Hamiltonian, so we would have a total j, which is 1. So we would have states with nj equal to -1, 0, and 1. So we're going to have a 3 by 3 matrix. And you can show that this matrix, when we have j equal to 1, with the Lipkin model, is going to be given by a minus epsilon, a 0, a minus v, and then it's going to be 0, 0, minus v, 0, and epsilon. And now you see very clearly that there is no point in dealing with free vectors, right? So I can reduce this to 2 basis states. And what you're going to see is that if I act with this Hamiltonian on the state, which I'm going to call so this is not the qubit state. This is a state with h, mj. And I will have combinations of these states, which are 1, -1, 1, 0, and 1 and +1. So if I act with h on 1, -1, I'm going to get minus epsilon of 1, -1, minus v times 1, 1. And if I act on this with 1, 0, you will see that that is 0, which we also have in here. And then if I take the h of 1 of +1, what I'm getting then is epsilon times 1, 1, minus v. So I leave that as a small exercise. But that means that what I could do now is simply to say that I don't need 3 states. I could just take qubit 0 and qubit 1. So this is the way we would analyze a problem here. So what I could say now, when I have this problem which is being simplified, and I'm going to show you how simple this problem becomes. So what I could say now is that, not that one, this is the last thing I will do now, and we will discuss this a little bit next time. I can let this be represented by qubit 0. And then I can take the 1, 1, which are the only relevant ones, and I let that be represented by qubit 1. So I can take a system which originally was a 2-particle system, and if I were to run this in a brute force way, I would think of using 2 qubits. So I would translate everything into a 4 by 4 matrix and blah, blah, blah. But I can now think of this as just a 1 qubit system. And that means that this Hamiltonian for j equal to 1 can then be rewritten as a minus epsilon times the Pauli Z matrix minus v times the Pauli X matrix. So if you feel a challenge and you want to include W, this obviously makes life a little bit more complicated. But for the project here, we can actually leave that term out because that's going to simplify everything. And it's going to simplify life for the 5 by 5 case, because when we put that away, we need only 3 basis states. And that could be 0, 0, 1, 1, or either 1, 0 or 0, 1. And then we get a simpler Hamiltonian to deal with. But you see, this one is pretty close to the first simple Hamiltonian we've been dealing with. So when it comes to the project, if you've done that one, the first Hamiltonian, then you have essentially the Lipkin model for that case, without this W term. So I'm going to sneak in some additional details in the beginning of the next lecture. So